Next, I will show you some applications in ultrafast optics. Okay. There are too many, so I just pick up several representatives. Okay. The first one is time-resolved spectroscopy. You can find the relevant materials in chapter 9 of the textbook. Okay. It's actually very easy to be understood. Okay. For example, you have ultra-fast laser, very short pulse here. You have a beam splitter to split the input pulse into two replicas. Okay. The thicker line represents the pulse is stronger here. The thinner line means the pulse is weaker here. So the two arms have different powers. Okay. So let the stronger pulse, named the pump pulse, hit a test sample first. Then, at a later time, the weaker pulse, let's name it as the probe pulse, strike the test sample again. Okay? And the time difference can be controlled by this vibrational delay stage. Okay? So basically, this is nothing but a microsecond interferometer. The delay is controllable. Okay? So what happens in this test sample? For the when the pump pulse hits the test sample, let's assume some transition is kicked out. Okay? For example, if the test sample is a molecule like this, without any input light, the vibrational state is like this. Okay? And it has a certain vibrational period. Then you can, according to my previous explanation, you can identify what is the vibration state by measuring the transmission spectrum. Because this vibrational state corresponds to a resonance wavelength, say lambda 0. So you can measure the output spectrum. If there is a dip here at the lambda 0, I know at this moment, this test sample corresponds to this vibrational state. Okay? Then, when the pump pulse hits the test sample, the vibrational state will be changed from this one to another one like this. Okay? Say the resonance wavelength is shifted, so you can measure the output spectrum, see the shift of the dip from lambda 0 to lambda 1. Then you know at this moment you got a different vibrational state. Okay. And let's assume the transition from one state to another to the other lasts for some period of time. And the dynamics can be probed, right, by tracing the probe spectrum, right? Of course, you have to scan the delay to see the different temporal moments. Okay, so by using a very simple microsecond interferometer and spectrometer at the output, you can trace the transition of vibrational states, which would be impossible otherwise, because the transition is very quick, much faster than the traditional tool can catch up. And the light source is, the ultra-fast laser source is a possible solution. And actually, this is the concept. The idea is a Nobel Prize research work promoted by a physicist, Zewell. He earned the Nobel Prize in chemistry in 1999 by the time-resolved spectroscopy using ultra-fast lasers. Okay. So that's why the pioneers in ultra-fast optics, a lot of them are related to the chemistry instead of physics or engineering. 最早使用这个工具得到重要成果的是化学啊，所以早期的这些研究的相关人员跟化学的关联反而很深啊，原因在这里啊，他们拿去做了一个化学家很长久以来想知道的问题啊，这个化学反应发生之后 ，what happens from the beginning to the end? You can know the input, you can easily know the output, but you have no idea what happened in between. It's too fast until this technique was introduced to chemistry. Any question? No? Good. Second application, coherent X-ray generation. Okay. Do you know X-ray? Yes. Have you ever used X-ray? I think so. I use it. When I got sick, the doctor asked me to shine some X-ray. Okay. But X-ray should be a very old technology, right? As early as 1900, the first Nobel Prize in physics was awarded to X-ray, right? 伦琴，对不对？ So what's new? Until very recently, the X-ray source you can get are incoherent X-ray, the X-ray bulb, just like the X-ray you use in hospitals. It can penetrate your body to see your lungs, your stomachs, or your bones, but it has no very good spatial resolution, right? Because your organs are pretty big, okay, centimeters at least. But if you want to use, if you want to have nanometer scale spatial resolution, you need coherent X-ray instead of incoherent X-ray. But it's very difficult to get coherent X-ray or X-ray laser. This is one of the possibilities. Based on the so-called 3-step model. Okay, some of you must have been familiar with this one, but I still try to explain it shortly. Step 1, strong infrared laser field. How strong? About 10 to the 14th watt per centimeter square. This number previously was pretty high, but nowadays more and more people can do that easily. Okay? And you need this infrared laser field to free the electrons, like this figure, without any external electric field. Your potential well should be like this, right? So your electron is well confined in this potential well. But in the presence of external electric field, like the light field, okay, your potential well will be strongly distorted. If the distortion is very large, then the electron is no longer well confined. It's possible to be released, okay, kicked out. But if your laser field is too strong, much larger than this number, then nothing special. Your electron will be kicked out and all the way never come back. So nothing cool will happen. But if your field is suitable, and you know the electric field is AC field, you have positive field, negative field, positive field, and so forth, then something interesting will happen. After releasing, it will not go away. To the other half cycle, the sign of electric field is reversed. So the kicking out force becomes the drawing back force, right? So your electron will come back to the mother atom. So when it comes back, combined with your mother atom, the kinetic energy of the electron will be released as a high photon energy. So if the kinetic energy is really high, the released photon energy can be very high as the X-ray photon energy. Okay, then you got the coherent X-ray. Okay, so step 1, infrared frees the electron. Step 2, electron is accelerated, pulled back. And step 3, the energetic electron combines with the mother atom. Then the kinetic energy is released as an X-ray photon. Okay, so this is a simplified 3-step model to explain why you can get coherent X-ray by shining a strong infrared laser. So you can see there is an exchange of energy from low photon energy infrared laser to high photon energy X-ray laser. Okay, by way of the nonlinear interaction with materials. Okay, and I show you one example. This experiment was carried out by Professor Chen Mingzhang's group several years before. If you look at the purple spectrum, you can see the cutoff, the highest photon energy is as high as 1.6 kilo electron volt, 1600个电子伏特. The corresponding wavelength is less than 1 nanometer. Okay? If you combine the input light source, the wavelength is 3.9 micron, which is mid-infrared laser. Comparing these two numbers, you can see it's about 5,000 harmonic. That means you have to combine 5,000 input photons to release a single output photon. Okay. You might be familiar with second harmonic generation or third harmonic generation, but it involves only 2 or 3 photons only. In this case, it involves with 5,000 photons. Okay, so it's a strong nonlinear optics, non-perturbative nonlinear optics. Any question? Okay. Another example is about biomicroscopy. We know life science is very popular nowadays. So how can ultrafast lasers contribute to the research in life science? This is one example. In vivo biomicroscopy. What is the meaning of in vivo? Do you know that? It's not English. Of course, not Mandarin. It's Latin. What is in vivo? Okay. 活体. It means these images were taken when the life, when it's still alive. Okay, not dead. For the research in life science, in vivo is extremely important. Of course, you can go autopsy, 你可以解剖, but it's already dead. You can know the structure, but you cannot know the mechanism. 对不对？它还活的时候怎么运作就无从得知了。活体的时候直接取像很重要啊。It's one of the feasible techniques that can do that. So what does this picture means? It means from the surface down to 1,000 microns or 1 millimeters, you can see everything, or even deeper than 1 millimeter depth. You can see the structures of different compositions when it is still alive. Okay. But why is it possible? If you want to take a 3-dimensional image like this, you need X, Y, and Z, right? You need 3 axes. X, Y are very straightforward, right? You just need to focus your laser beam and scan the spot. You can have XY resolution. But how do you get Z resolution, the depth resolution? And then when it is still alive, how can you do that? Usually, the researcher in life science rely on some fluorophore, for example, the red fluorescence protein or RFP, to label the specific targets of interest. 他们想观察的东西，要先用这个不同的染料介质，这些染料会附着在他想看的东西，这是第一步。But usually the fluorophore can be excited by visible light or UV light. Okay? For example, RFP means the fluorescence is red light. 它发出来的是红光，红色的荧光。And the excitation wavelength has to be even shorter than the red light, so it can be excited by green lasers or even UV lasers. Okay? But if you directly use visible lasers to shine the target, you will have no Z resolution. Because on the way from the laser beam to the focus, anything will be excited along the path. So the image you captured is the integration of every different depths. 所以你照一道绿光雷射好了，照下来这个病虽然越来越小，但是整条路径上所有的红荧光蛋白都被你激发了，它们都发红光，然后你把它捕捉下来，你会不会只看到一点 ？No. You know, you only capture the integration signal. So then you have no depth resolution. But if you shine your infrared laser beams, things are very different. For example, if you use 100 femtosecond 20 nanojoule pulse, the peak power is about 200 kilowatts at this wavelength, 1675 nanometers. The wavelength is very long, much longer than the red light. So in principle, this laser will not excite RFP, right? Have you get lost? Maybe I have to slow down. 简单说一下，因为时间差不多到了哈。这个荧光怎么来的？你先要用一个短波长或者光子能量比较高的光去激发它，跃迁到高能阶，对不对？然后掉下来，它没有掉那么多，所以发出来的波长会比较长。发出来是红光，那你激发光可能就是绿光或更短的波长。好，这个即使是红光都已经是600-700纳米，我拿这么长的波长去打它有用吗？理论上没用，对不对？它应该是透明的。你怎么打，它都不发荧光。But if you shine the RFP with instead of a CW laser at this wavelength, but a femtosecond laser at this wavelength, things are different because for femtosecond lasers, the photon density is very high, so it's possible that 2 or even 3 photons can combine together simultaneously. Then the total photon energy now is big enough to excite RFP. For example, if you combine 3 photons at this wavelength, the equivalent wavelength should be 1675 divided by 3, right? 等效的波长就变成多少？500多纳米。It's green light. Then it can excite the fluorophore, but not all the way to the focal point, but only in the vicinity of the focal point. 只有在焦点附近，那个光强度大到可以让一次3颗 photon combine 激发，其他都没有。Then you got the depth resolution. Okay, So that's the working principle of this application. Okay, so I think we have to stop here today now.